Welcome, everyone. My name's Eric. Thank you for sticking around until the very end of the day to hang out with me. I know it's a completely different time zone for you. And the reason I know it's a completely different time zone for you is because yesterday I got to wake up at 1 in the morning and teach for 8 hours. And that was interesting. I felt like I was drunk the whole time. And not because I was drunk, just because sleep was very, very weird that night. Today we're going to be going through one of my favorite presentations, a SQL Server performance tuning tasting menu. And the reason I call it that is because there's no real rhyme or reason to it. There's no real form to it. It's just kind of whatever set of demos I have, I've been working on writing lately that I think are interesting. And it's just sort of like, a little small bite, walk through things that I think are kind of fun and quirky about SQL Server at the moment. If you want to get in touch with me, if there's anything that you have questions about, that you are crazy interested in learning about, you can get in touch with me here. That's ericdarlingdata.com, Eric at Erik Darling Data. That's my email address. I'm pretty sure that's my email address. And then if you want to get in touch with me on Twitter, at Erik Darling Data, there's a very common theme there. It's all my name. So at this point, I'm pretty hard to miss as far as those things go. Anyway, let's get rid of this and let's start talking about something more interesting than me. Let's talk first about trivial plans. Now, trivial plans are a very interesting, little short circuit for the optimizer. When things are just so obvious about which index to use, about how to run a query, there's no decision to make about what plan might cost more or less, then SQL Server can just say, just take this one and go. It really doesn't have to put a ton of thought into it, and it really doesn't have to, spend a lot of time sort of coming up with the best plan as quickly as possible for you. So when you want to figure out if you are getting a trivial plan, you have to first look at an execution plan, which I suppose makes sense. But when you look at an execution plan, and this is something you should always be doing anyway, either right-click and hit properties or hit the F4 key, because what pops up over to the side is this little properties window, and this properties window gives you far more information than what you get from these silly little tooltips. I mean, there's like okay information in the tooltips, but like this properties window is really where you get all the good stuff. And if you look right about here, you'll see this optimization level line. You can see that this query has received a trivial execution plan. And the reason that it did is because SQL Server didn't have any decisions to make about how to do this. There's one index on the table, that's the clustered index. We're asking for the top 100 rows, and SQL Server is just like, yeah, sure, take them. Here's a top, here's a clustered index scan, go take your rows and go. I don't need to think any more about it. It's a little bit small. It's a little big for my tastes. Now we can see everything. Most things. Let's make that a little bit smaller, and let's not jump around too much. Now, you can do some pretty funny things, and you can still end up with a trivial plan. For example, I'm going to take the top 10,000 rows from the users table, and I'm going to generate a row number over those 10,000 rows. And yet SQL Server still insists that there are no two ways to do this. There is just one way to do this, and it is trivial to do it. I think it's almost like an insult. It's just like this query. Trivial. I don't need to think about this at all. But there are some things that we have when things get spiced up a little bit. When we all of a sudden have some cost-based decisions to make, then SQL Server will have to get up off its lazy butt and start thinking about the best way to do things. Now, if I want to get a distinct top 1,000 from the users table, you would think that SQL Server might have to use its brain and come up with a really good way to do this, because I am selecting a whole bunch of columns from the users table. And if you see that there are a whole bunch of columns there, some of them are text, some of them are null, there's dates and all that other stuff. But when we look at the execution plan details, we still have a trivial plan. And we still have a trivial plan because the users table has a primary key on it. And the primary key means that no matter what 10,000 rows we give you, they will be unique because that primary key is a unique set of values. So SQL Server doesn't even have to think too much about this. But then if we start selecting non-unique columns, right, we don't have that uniqueifier in our data, all of a sudden SQL Server has some choices to make. And when we have choices to make, we might get different execution plans. For example, if we have a top 1,000 or a top 5,000, SQL Server might choose to do things differently in those cases. So the top 1,000 rows, SQL Server says, I can use a hash match flow distinct here. I think that'll be relatively cheap. And for the top 5,000, SQL Server says, no, we're going to have to aggregate the whole thing. So SQL Server made a choice. And when SQL Server has to make choices, that's when you start seeing plans get fully optimized. You can see the optimization level is full there, and the optimization level will, of course, be full here because SQL Server made a choice on how to aggregate this data. It could have used a sort and a stream aggregate. It could have, I don't know. I think actually that about exhausts it. I guess it could have used this sort distinct on there, but that is how SQL Server decided to give us a unique, or rather a distinct number of rows. Now, there are some obvious things that will get full optimization, like joins, subqueries, exist, not exist, like anything where SQL Server really has to jump in and like make decisions. Now, if we have to do, sometimes if we ask for an order by without an index, SQL Server won't have a ton of choices. But if the query is expensive enough, if the query costs enough to go parallel, if SQL Server looks at how much work a query will have to do just to run, SQL Server might say, we might be better off using multiple cores to do it. And when that happens, we look at the properties and we can see that SQL Server has fully optimized this plan, despite the fact that it didn't have to make a ton of choices about what to do here. It just looked at the amount of work that the query had to do and decided that it needed a parallel plan. So another thing that will that tells you if a query has been fully optimized or not is if SQL Server has chosen a parallel plan rather than a serial plan. Part of what makes a plan trivial is that the cost of the query can't be higher than your cost threshold for parallelism setting. If it is, you do not have a trivial plan. You do not have a trivial query anymore, and you will not have a trivial plan. Now, there are some really funny things that will keep you from having a trivial plan. Now, look at these two queries. One of them just selects ID, and one of them selects select ID in parentheses. Now, you would think that this wouldn't change much about the optimizer. You would think that something inside the optimizer's brain would say, I know what that is, and just sort of flush it away. But no, SQL Server is apparently just not that smart. Despite like 40 years of PhD students working on this thing, we still have to compute that select ID. Isn't that weird? And if we look at the execution plan details, this select query has a trivial optimization level, and this select query has a full optimization level. SQL Server put its whole brain behind this thing, and all it came up with was a compute scalar. It's bizarre. Now, there's also another simple subquery that you would think would make no difference to a mature, smart person like SQL Server. But what happened? We run this, we get the exact same results back. Nothing about what we're doing here will logically change the answer to this query. 1 equals select 1 is always going to equal 1 equals select 1. But SQL Server, being the crazy person that it is, decides that one of these plans will be trivial, and 1 equals select 1 requires the full weight of optimization. And that's just weird. Okay. Now, I've been talking a lot about what makes a trivial plan. Let's talk a little bit about when or why a trivial plan might matter. When you have a trivial plan, you might miss out on some optimizations because SQL Server isn't going further along in its process and exploring things. One of those is missing index requests. If I run these two queries, they are identical in logic. They will not return different results on any planet. I don't know, maybe if there's a quantum computer and like a supernova goes off nearby, things might get a little awkward for this one. But in like, most normal computing systems, 1 equals select 1 is always going to equal 1 equals. There's not like a Schrodinger's 1 in those parentheses. So when we look at these two execution plans, things are a little bit different between them. You can see that top query looks a little bit different than the way we wrote it. You got some parentheses in there. Our reputation equals 2 has been turned into reputation equals @1, which means that we have not only received a trivial plan, but we have also received simple parameterization. And if we look at this bottom query, we can see that SQL Server has given us the query, well, the way we wrote it, we have reputation equals 2 and 1 equals select 1. And we also have a missing index request. SQL Server has decided that maybe, just maybe, an index could help us avoid having to read 2.4 million rows in order to find 1,800 rows. Up here, SQL Server is just like, nah, no index could possibly help. We could not possibly do any better than we have done. You're an idiot. Go sit down. Trust me. It's an interesting choice, SQL Server. Interesting choice indeed. Another place where trivial plans can be a real bummer is when we are good, diligent DBAs and developers and SQL database people. And what do? We create constraints. And why do we create constraints? We create constraints because we care about the integrity of our data. And we want SQL Server to know things about our data so that it can make better decisions about them. Now, I just created this constraint. At least I'm pretty sure I did. I'm just make sure I hit F5. Whew. All right, cool. Done. It's been a weird couple of days. Now, what I want you to know is that I just created this constraint, and there are no rabbits up my sleeve. This constraint is not trusted. It's a weird sort of double negative there, right? It should just be is trusted. I don't know what is not trusted has to be a thing. An odd choice. I don't know what notation that is. I don't like it though. But SQL Server, knowing that every value in the user's table for reputation is greater than or equal to 1 and less than or equal to 2 million, it should know that if I run a query for a reputation equals 0, it should not have to do any work. And yet here we are again with this simple parameterization and with this trivial plan and with this full clustered index scan. If we look at what SQL Server did, we still read all 2.4 million rows to figure out that we didn't have anything in there. And if we look at the amount of I/O that SQL Server did when this query ran, it read the entire clustered index, all 44,443 pages of it. Okay, SQL Server, bold choice, bold choice. Now, what happens if we give SQL Server a little bit more time to think about things? Well, that finished pretty quickly. If we look at the execution plan, we no longer have a clustered index scan. We have a constant scan. SQL Server knew well enough what it had to do, and it did. It said, there is no such thing as a 0 in this table. I'm not going to bother touching the table. We did no I/O. There's no CPU. If we go look at the properties, I forget why I closed that. That was very silly of me, which we have absolutely nothing going on in here. There's no batches, no rows, no rebinds, no rewinds, no actual time. We have zeros all down the line. SQL Server did no work here. Now, SQL Server did work here because of what happened to the execution plan, or rather what happened to the query. The query was simple parameterized, and because it was simply parameterized, what happens is SQL Server had to come up with an execution plan that could be safe for whatever literal value becomes a parameter. We could have 1, 2, 3, 4, 5 through up through 2 million. Actually, I guess through the integer max we could have in there, since reputation is an integer. So SQL Server had to come up with an execution plan that would be okay for any integer value. And because it had to come up with a safe execution plan, and it had to cache that execution plan for reuse, it had to scan the clustered index, because what else could it do? We couldn't constant scan if we picked a valid value. SQL Server, you're weird sometimes. So trivial plans tend to pair well if you have no real design specification for your system, if you don't have any constraints, and if you already have perfect indexes. Otherwise, trivial plans can hide a lot and can keep the SQL Server optimizer from doing its job and giving you the best execution, or rather a better execution plan than maybe you could come up with on your own, even if you just had a bunch of crayons. Now let's talk about, I don't see any questions, so I'm just going to plow through until questions show up. So if there are no questions, I'm just going to move seamlessly to the next demo. This will be the only interruption. Let's talk a little bit about how read queries can block write queries and why read committed is the worst isolation level. I'm not kidding. Like, so everyone makes fun of no lock. Everyone always makes fun of read uncommitted, no lock, queries that don't take any locks when they run. But what no one seems to realize is that read committed is really not that much better from read uncommitted. Now, there is a question from Robert. It says, do you always add that clause 1 equals select 1 in order to make SQL Server think better? Not always, only if I see that I've gotten a trivial plan. Otherwise, usually the queries that I'm working on are not ones that are anywhere near trivial. All right, so let's look at how read queries can block write queries. So I've got this stored procedure here, and it is aptly titled read blocker, right? And what we're going to do is we are going to get an execution plan put into the cache for this query for a very, very selective set of data, right? The Stack Overflow database that I'm working on right here, Stack Overflow 2013, only has data through December 31st of 2013. After that, there is nothing. We have chopped off all of the data from there. So if we run this query that's looking for creation dates, and we run that for a very selective set of data, we are going to get back a query plan that looks like this, that has an index seek into our index, and then does a key lookup to go get some other stuff out of the table. And if we look at what that key lookup is going to fetch, it is just the post ID column. So for every row that comes out of this clustered index seek, SQL Server needs to go and do a key lookup to go get that post ID column. Yes, I'm using SQL Server 2019. That's patched up to CU8 too. So there you go. So if we run that query, right, when we got that plan put into cache and we rerun this query, this is going to take a significantly longer amount of time to run because we're going to reuse that execution plan with the key lookups, but we are going to be finding data from all the way back to the beginning of when date time started. Not when time started, just when date time started, which is when we switched over to this newfangled calendar after the English Calendar Revolution Wars or something like that. I forget exactly what it is. But we need to open up some new windows because we need to explore things further. So what we're going to do is come over here, and we are going to start running our stored procedure from that start date, which is pretty far back. And then we're going to come over here, and we're going to try to run this update. And now we're going to come over here, and we're going to look at SP who is active, and we're going to see that we have a read query blocking a write query. Isn't that something? We have our select up here. We have our update down here, and we have our update waiting to get an intent exclusive lock. Crazy, isn't it? Now, if we go look at the details of what SQL Server is trying to lock, I can actually get rid of this. We don't need this thing continuing to run and being goofy. If we go look at the details of the lock, so if we run SP who is active with this get locks equals 1 parameter, we'll get this clickable column of details about what got locked and when. Now, we can see that the modification query, as soon as we get rid of some of this goofy stuff, is waiting to take a lock on the votes table, an object level lock, an intent exclusive lock, and we are waiting to get that lock. We are stuck waiting to take that lock. The reason we're stuck waiting to take that lock is because we have this lock on the votes table already. Right? You can see the votes table locked here. You can see it's an object level lock, and we see the request mode equals S. It is a shared object level lock. I don't know why we have a database encryption scan. I have no encryption going on. I think SQL Server is being a bit silly, but we can see that this request has been granted. And so right now, something about our read query has taken an object level lock on the votes table. And what that is let me get rid of these windows real quick. What that is in our execution plan, SQL Server, under the read committed isolation level, has to guarantee that whatever rows it ends up finding here have to be here. See, a key lookup it really is just a join between a non-clustered index and a clustered index. If we look closely at what the key lookup does, you'll see something kind of funny. Oops, you'll see something kind of funny. Come on, tooltip, work with me. Down here, you'll see the seek predicate, and the seek predicate is going to tell us what the relationship is between the clustered and non-clustered index. So SQL Server, when you create a non-clustered index on a table that has a clustered index on it, that non-clustered index will inherit the clustered index key columns. And then so you can do things like this. So as SQL Server is finding rows here, we have to make sure that those rows don't disappear from here, meaning they don't get updated, they don't get deleted, they don't get, like, something doesn't happen to them, right? So SQL Server has, when you see a key lookup, SQL Server has to take a lock on the clustered index for the duration of the query. If we had kept hitting F5, we could have seen about 12 seconds of blocking rather, between the read query and the write query while this thing runs. Now, you could maybe fix this in a couple different ways. You could create a covering index. Right now, our index is on creation date and vote type ID. If we included post type ID and we didn't need to do a key lookup here, we could avoid that situation. We could also use an optimistic isolation level like read committed snapshot isolation or snapshot isolation. And those will both prevent that particular phenomena from happening. We could also rewrite our query to do a self join and use a merge or hash join hint so that SQL Server would not do a nested loops join and need to take an object level lock on the inner side of the nested loops join and lock the object for the duration. So that's one reason why I hate read committed the isolation level. Another reason why I hate read committed the isolation level is because not only can read queries block update queries, but we can also have weird deadlocks between read queries and write queries. So I'm going to do something pretty similar to what I did last time, except this is a little bit more of a brute force attack. Actually, I guess the last one was a pretty well a brute force attack too. I just made a query terrible and intentionally gave it a bad execution plan. I guess that's pretty brute force as well. But let's grab some stuff from here. And what we're going to do is run this update, and this update query is essentially going to flip vote type ID between 8 and 0 for this one ID. And this read query is going to try to select post IDs for where vote type ID equals 8. And if well, actually, I have to time this perfectly. So I have to come over here, and I have to start the update, and then I have to come over here, and I have to start the select, and then I have to come over here and hit SB who is active. And for a brief moment in time, before SQL Server kills our read query and says, I'm going to deadlock you, we have this very cool painting. Now, I'm going to move this blocking session ID column over next to the session ID column. And I'm going to move this wait info column over here. And what we're going to see is something very cool. This is in the moments just before a deadlock explodes. We can see session ID 55 is blocked by session ID 66. We can see that session ID 66 is blocked by session ID 55. We can see that the queries involved are our update and select, and they are indeed blocking each other. They are locked with each other. They cannot make progress because of each other. All right? Pretty crazy. So let's get rid of this. Let's get rid of this. We don't need this anymore, I don't think. That seems to have finished. And if we come back over here and look at what the select query window, you can see that SQL Server has decided to choose our select query as the victim of a deadlock. our select query could not carry on and do anything. And the reason that it couldn't is a very similar reason to the one that we just saw. This query would have to do a key lookup and try to get data from two different places. It would have to take that object level lock again on the inner side of the key lookup, and the update query. You can see, well, actually, we should show this point this out first. Where you have to seek into here, and we have to seek into here to get that data, right? So we have the non-clustered index that we created and the clustered index on this table being read and locked for different portions of the read operation. And then we have this update query, and the update query is going to have to read the clustered index, and then it's going to have to update both the clustered index and the non-clustered index on our table. So we have these two queries that are just like kind of fighting each other with these reads and these writes. And if that happens enough, SQL Server just says, enough of you, and it kills our select query. Now, again, we could fix this with a covering index. If we had post type ID in our index and we didn't need to do the key lookup in our read query, we could avoid this issue. And of course, this pretty much the same things as last time as well. If we created a covering index, used an optimistic isolation level, or if we rewrote the query in sort of a strange and funny way, then we would not need to take the same locks, and we could avoid that same situation. Of course, when we use the join hints in these situations, the read query does slow down a bit, and that does make things a little questionable there. But as long as you're not running things in a 10,000 iteration loop, you'll probably be all right. I say probably, but who knows? SQL Server is a dangerous place. All right. Don't see any questions, but I'll go back if there are. So now it's time to talk about top and parameters. I see a lot of people out there in the wild world who write queries, and they want to give users the ability to return a specific number of rows, and they use top, and they want to give top a parameter to do it. So if we run this query, where we're asking for the top 38 users from the users table who have a reputation over 10,000, and order that by reputation descending. And we want to get the most recent badge for all of those users. This query will run, and it doesn't have any helpful indexes. It takes about 9 seconds. We go look at the execution. Oh, I didn't grab the execution plan while I was talking. Oh, that silly time. Oh, that silly time of me. So this query is at least fairly simple in what we're asking. Yeah, like the question that we're asking of SQL Server. Just give me the most recent badge for all of these high-value users, and we'll get that list back. And if we look at the execution plan, we'll see that we spent about 9 and a half seconds of our lives running this. You can see the nice operator times and SSMS 18.6 over here. And if we look at this section of the execution plan, we can see that this really is where we spent the majority of our time, just scanning this clustered index over and over again, which is not ideal, but I guarantee you that 10 seconds is better than what would happen if we parameterized this top. All right, so if we create a store procedure and we do the exact same thing here, we say select top at top, and we have, actually, there's nothing else different about this query. All we did was stick a top in there. If I run this, we'll be sitting here for a while. So I'm not going to run this. I'm just going to show you a saved version of the execution plan. And let me zoom this to fit so that we can all live and laugh and love together. Because where we used to spend 9 seconds scanning a clustered index, now we spend 1 minute and 16 seconds doing the same exact thing. All we did was parameterize the top. Now, this is a rather unfortunate situation. What happens is, if you use a literal value for top and it's small, SQL Server can let buffers go the second they get 1 row in them. If you parameterize top, and SQL Server doesn't really have any idea what top might be, could be big one time, could be little another time, SQL Server has to wait for buffers to fill up and then get passed on. And it turns out that can be a time-consuming process. When we sent one row, when we took a buffer and sent one row, we finished in 10 seconds. When we waited for pages to fill up buffers, we waited 1 minute and 16 seconds. That seems less than ideal to me. Now, one way that we can sort of get around this behavior is by telling SQL Server to optimize top for 1. So if we run this and we create this store procedure, we're doing the same exact thing with top here, good stuff, and we rerun this, it will take 10 seconds again. SQL Server will allow the optimization where we no longer have to wait for buffers to fill up, and we just send them when a row comes, and we'll get just about the exact same execution plan that we got when we ran this with a literal top 38. I guess it took half a second longer. Sorry. Maybe that was coming up with an execution plan or something. Who knows? But like that's one way to get around this sort of weird behavior. Another way to get around this sort of weird behavior is to make SQL Server, rather than do a nested loops join with like lots of little scans, to make SQL Server do one big scan of the data. And we can do that by asking for a top 1 in a slightly different way. If we ask for SQL Server to figure out what the most recent badge was by generating a row number and then filtering that row number for a specific user, then SQL Server can do the same thing. And actually, if I'm remembering this correctly, this actually runs a little bit faster than doing it the other way, only because there are no useful indexes. Yeah, this runs in about 4 seconds. And you can see that SQL Server chooses a hash join up here rather than a nested loops join. And down here, we just have one big scan of the data rather than a bunch of little scans. And then SQL Server can just go in and get stuff. And pages and buffers tend to fill up pretty quickly when we just do one big scan rather than if we do a bunch of nested loops joins. So that was fun. And I ran into this while I was working with a client, and it was perplexing for a little while. And but we got it worked out. And I thought, you know what, I'm going to write this demo. I don't know who that one person out there is whose life this is going to change, but someone out there is going to have run into this, and someone out there is going to freak out when they parameterize a top and their queries start running 10 times slower. And that's the person who I'm here for. I know you're out there somewhere. You're welcome. Now, we could fix this in a couple different ways. We could create an index, but that's sort of boring. Anyone can create an index. And we can also optimize for a top, and we can also, optimize for a top 1. And we can also rewrite the query a little bit. I forgot to, oh, look at that. Should have hit enter a few more times there. Formatting is everything. So there's a deeper explanation. I wrote a blog post about this. There's a deeper explanation if you want to head over here and check that out. And I'm here. Yes, I'm here too. Of course, that happens because when you use a top with a constant and the constant is small, then exchange packets are allowed to send earlier than they are if you parameterize a top, because SQL Server has to, again, this comes down to a plan safety issue. SQL Server has to come up with a plan that is safe for if you send, so like what I think what a lot of people forget is that the largest value you can put into a top is the big int max, which is 9 point this number. I don't even know what to call that number. Is that trillions? I don't know. 9.2 trillion, I guess. So SQL Server has to come up with an execution plan that's safe for if you say, I want the big int max. It has to figure that out. SQL Server is so crazy. All right, let's get rid of those. And we just used a windowing function. We used a row number to generate some rows and filter on that. And that turned out pretty good for that query. But now we need to ask SQL Server a slightly different question. And it's a place where windowing functions, at least right now, in SQL Server are really deficient. It would be awesome if we could ask SQL Server to, in a windowing function, count distinct values, but we can't. SQL Server is incapable of counting distinct values when we use the over clause. If you would like to vote for that, I think it's Itzik, so it's safe to vote for him. Right? He's a nice guy. You can go to bit.ly and count distinct, please. That take you over to the user voice item where you can vote for this if you're into that sort of thing. If not, or if you'd rather just hang out with me for a minute, we can talk about a way to write this query that will actually work in SQL Server. And we once again have to go back to using our friend apply. So what we'll do is we'll get a count of distinct values of distinct scores from the comments table joined to itself. We're going to take the comments table and apply the comments table to itself. We're really going to lay into that comments table, get in there. And we're going to correlate that on user ID, and we're just going to ask for where the score is greater than 1. I forget why. There was probably a good reason for that. I don't know. But when we run this query, we're going to be disappointed. Not because it doesn't work. This works, and it returns correct results. What we're going to be disappointed by is the fact that it takes a long time. Look at this. SQL Server took about 4.5 seconds to run this query. Why? Because it made some bad choices. We'll talk about those choices in a minute. For right now, I want to show you how to rewrite this query so that SQL Server makes better choices. We can do that by adding in this redundant group by. So if we tell SQL Server to group by user ID, even though we're correlating on user ID, SQL Server will make a completely different set of choices, and we will get a plan that no longer takes 4.5 seconds, but actually takes just about 1 second, or 1.3 seconds. Okay, sorry. I will give you a coupon for your 300 milliseconds. But we got a slightly different execution plan, and what I want to do is, rather than sit there and stare at that, let's look at the differences between these two plans. Now, up top is the query, the way it was written originally, where there is no redundant group by here. And down here, this is where we have a redundant group by. And let's look at the different choices SQL Server made. Now, it was so close. It was so close. It was so profoundly close to making good choices all along the way, but it did not. We scan in both places. We repartition streams in both places. We aggregate streams in both places. We repartition streams again. We hash again. But now SQL Server did something different. And you can see where this bad choice was now. Way early on, SQL Server decided to filter things out. If we look at our queries, we have this filter here, and that filter is on distinct score count, right? So we generate this count inside of the apply, and we filter on it outside of the apply. In the first query, SQL Server did something really dumb. Took this whole table, took everything from here, joined it together, and then filtered afterwards from 9598465 down to 50,000 rows. In this query, SQL Server made a much smarter choice and filtered stuff down way earlier. So we had far fewer rows going into the join. Interesting, right? Interesting how malleable SQL Server is. So windowing functions, at least in SQL Server, sort of have a long way to go. There's a lot of linguistic capabilities that are missing from them that are present in even free databases like Postgres. Of course, Oracle has a ton of stuff in DB2. I mean, all 3 people who use DB2 are really happy with windowing functions. But there's very limited support for common needs, and we often need clever rewrites to work around those limitations, and even more clever rewrites in order to get them to perform well. And that also includes indexing. So let's talk about another area where the optimizer is a little bit short-sighted. It really screwed us up there if we didn't like force it to group by user ID. It was really just bizarre the way that worked. Let's talk about another place where the optimizer gets a little bit weird, and that's with some implied predicates. Now, the optimizer is generally good at doing this most of the time. If we take this query and let's turn on execution plans, let's run this. This is going to return very quickly. And the query is pretty simple. We're joining post to comments on these user ID columns, and we're filtering just down to one specific user 22656. Now, luckily for us, our where clause column is filtering to a single value that is also in our join condition. How lucky is that? Now let's look at the execution plan for this. SQL Server is telling us something. SQL Server is telling us something bad is happening here. Of course, SQL Server is wrong. SQL Server is going to tell us that we don't have a join predicate when we most certainly do have a join predicate. We have a join predicate right here. That is literally a join predicate. Like, you don't get any more join predicate than that. The reason why SQL Server doesn't think that there's a join predicate is because there's nothing here that gives it that. But if we look at this clustered index scan, we can see a predicate here for where user ID equals 22656. And if we look here, we can see a predicate for where owner user ID equals 22656. So we went and found the only values that could possibly match. And when we bring those values to this nested loops join, they have no choice but to match because the predicate is pushed down to where we touch the indexes. But because we have this summer intern query plan warning, SQL Server tells us we don't have a join predicate. Most of the time when I see this, I ignore it. It's pretty dumb. Now, where SQL Server does a slightly worse job is when we have a where clause with ORs that that span tables rather. So we're going to join comments to votes, and we're going to join them on the post ID column. Right? Pretty good there. Join on post ID, and our where clause is going to be where c.postid equals 138, which, since we're joining on this, should be doable. But we're also going to say, well, if the voter user ID is 831, we can also let that in. And if we run this, it's going to take a little while. There's a question in chat. So is it some rule that it matters where clauses put this outside inside subqueries? You're going to have to ask that in a more concise way. I'm not sure what you're getting at there. Sorry about that. But let's look at this query plan. So we have an index scan up here, and we have an index scan down here. And we just saw index scans where predicates were applied. And if we look, there is no predicate here whatsoever. And there is no predicate here whatsoever. Why not? We were just able to take predicates in our where clause and push them to when we touched indexes. Where are they now? Where'd they go? I want to know what you're beeping at. So if we look at our hash join, we not only see where we're asking where columns are, but we also see right here, we're asking for those predicates to be applied. Did you answer the question, what are you using? Yes, I'm on SQL Server 2019. All right, so we can see that SQL Server did not do such a good job of applying predicates in this case. Right? SQL Server was not able to take these and push them down to where it should have, so that we could have used, or we could have, I don't know, done fewer reads, done less work, all that stuff. But if we change our query a little bit to just ask it where user ID equals 831, then all of a sudden SQL Server will be able to make much better choices, not have a query that runs for 11 seconds, and will be able to push predicates and seek to those predicates very, very easily. So I see this a lot in entity framework queries where, we'll have this sort of or where you can do or this or that or this or this or that or the other thing. And SQL Server, we'll end up with these execution plans where predicates just don't get pushed down to where we touched and down to where we touch the indexes. All it does is scan the entire thing, and it's not a good time for anyone. Right, so this query took about 9.5 seconds, and it's all because SQL Server decided that it was unable to push predicates down to where we cared about them. So that's not a good time. And while we're talking about pushing things, let's talk about where bitmaps can be pushed to, because this is a fun one. This is a fun one. Someone says, thanks for the hint. You're welcome. Don't know what hint that was, but enjoy it. Now, we're going to talk about bitmaps because a lot of the times when I do this talk in person and I get to say, so who loves bitmaps? Most people just stare at me blankly. And I say, oh, cool, what's a bitmap? Or like someone will raise their hand and be like, what's your favorite thing about bitmaps? And they'll be like, I don't know. They seem great. I read a book on computer science once. Bloom filters. So we have this query, and this query is going to select a count and do some grouping and other fun stuff. And then we're going to join the result of that down here. And the query plan that we get back, if we had turned on query plans, is going to be involve a bitmap. And that's going to be fun for everybody. And the reason that's going to be fun for everybody is because this is a very, very useful bitmap. All right, so when you have a parallel plan with a hash join or a merge join, SQL Server can use bitmap filters to filter out data. Isn't that exotic? Isn't that fun? Isn't she pretty in pink? But where bitmaps get created in the execution plan is not where they get used by SQL Server. They get created up here. So like we have to scan this table and we do some aggregating up front, but then we create a bitmap. And that bitmap is going to be on the values for user ID, because that's our join key. So what we do is we create the bitmap here, but then we use the bitmap way down over here. And we can see where SQL Server has a predicate. The bitmap is in row, and we can see just how useful this bitmap was. And we can see how useful it was by looking here. So SQL Server was able to filter out a whole lot of rows using that bitmap. We go from 24 million rows down to 40,000 rows by applying that bitmap filter. Cool. I like that. I like a nice, useful bitmap. Huh? Doesn't everyone? Now, the cool thing about bitmaps is they sort of work way, way further down than like where clauses and stuff. This thing really they really keep rows from like even just moving past the index scan. So that's a really nice thing about bitmaps. Where bitmaps are not so useful is when they look like this. Run this query. We already have query plans turned on, so we can't possibly lose anything here. But oh, look at this. Et voila, we have another bitmap get created. But now when we look at this clustered index scan, the number of rows that we read is not that far off from the number of rows that passed through. So this is a very, very useless bitmap. It's not a very good bitmap at all. This bitmap did not rule out many rows. It had very, very good intentions. This bitmap had the best of intentions, but it just did not help us eliminate too many rows. Now, bitmaps don't always get so lucky. Bitmaps do not always get down to where we scan our index. Sometimes bitmaps get a little bit held up. Now, it's not that they can't end up past aggregates here. It's just that sometimes they don't. SQL Server is like, I'm confused. SQL Server gets lost sometimes. It's okay. But if we look here, we have our bitmap. I don't know if this bitmap would have been more useful if it got pushed all the way down. I have no opinion on that. But if we look at the clustered index scan, we don't see anything at all about the bitmap. It's not there. It's bitmapless. And it's not like SQL Server just threw the bitmap away. It just applied the bitmap in a different place. So if we look at the repartition streams operator, now we see our bitmap appear. Why? I don't know. Databases are weird. I try not to ask too many questions. Speaking of weird, let's talk about spools. Because I hate spools. No, I don't hate spools. I just hate when queries are written so badly that they need spools. So let's reset this table, get to the point. Now, what we're going to do is update this table that I've created called total score by user. And what we want to do is find the maximum score in the table. So this score is split up between questions and answers. And I'll just take a top 100 from total score by user, just so you kind of get a feel for what the table looks like. We have user IDs, display names, their top question score, their top answer score, and I don't know, whatever, I forget what total score is, but anyway, the total score or the max score column is going to be what we're trying to fill with whichever is higher, question score or answer score. So we're going to take question scores for a user and the answer scores for a user. And we're going to ask SQL Server to find the highest one, and then we're going to update that column with whatever is higher. And this isn't going to be too fast. This is not a very quick update. 6, 7, 8, 8 seconds, 8 seconds and change, I guess. 8.3 seconds. All right. And if we look at the execution plan and we start trying to figure out where we spent our time, I mean, that's reasonably fast. 285 milliseconds, 287, 758, 1 second, second and a half, getting up to there. Okay. So let me go from a second and a half to 4.3 seconds. So if anyone wants to subtract 1.6 from 4.3, that's how long we took putting data into this spool. And then we took another 4 seconds, just about, updating this table from the eager table spool. So there's a pretty good chunk of time that we just spent, like sort of like right in here, right in here, right in here. Spent a long time doing that. And of course, we have this spool because our target table, the total score by user table, is the same as where we're trying to get rows to work from. All right. So because total score by user is the source and the target, this is starting to sound like a talk on merge, but don't worry, we're not going to get into that. So, but because it's the source and the target, we need this thing right here, this eager spool, to do Halloween protection so that we don't end up in like some infinite or some loop that overstays its welcome. Right. So we have to put data into that table spool, and putting data into table spools is often quite inefficient, but at least, our update worked. I don't know why we started returning rows outside of a grid. That's not fun, but we see our max score column is now filled up. Not for long though. We're gonna get rid of that. I'm going to get rid of that total score by user column, wipe that thing out. And what I'm going to do is, rather than just say, well, let's run our update all in one big chunk, what I'm going to do is I'm going to create a table, and I'm going to a temp table, and I'm going to fill that temp table up with the things that we care about. Right? So temp table, create temp table, ID, max score. We're going to insert the ID in the max score for then the same thing that we just got there. And then rather than just update everything all in one go, we're going to update everything from the temp table. And this is a bit quicker overall than what we got before, 3.2 seconds. And that's all because we do not need to do that we do not have a spool in here anymore. We do not need to do that separation. Why? Because we did it manually. We have manual phase separation. All right. So we go from like 8.5 seconds down to like, what was that again? 3.2 seconds to update that table, because we dumped some table into a temp table first, and we joined our final product to the table we were going to join to the table we're going to update, and we get to skip all of the nonsense there. So the reason why this is better is, again, like talked about it a minute ago, but when the table you're modifying is part of the from, right? When the table that's the target of a modification is also the source of modification, the optimizer often has to use a spool for Halloween protection to keep track of rows that it needs to modify so that you don't get stuck in an infinite loop. The temp table is generally a better way to do this because the manual phase separation, a phrase which I will never get tired of, loading data into temp tables is way more efficient than the way data gets loaded into spools. If you load data into a spool, it happens row by row, and you're missing a lot of the optimizations that have come to TempDB, putting data into temp tables, because spools are just dumb, old, and ugly, which is, I guess, something I'm going to stick by. So enjoy that. When you're doing modification queries and you have the target and the source and they're the same table, be careful, watch out for spools. Often putting things into a temp table is a much faster approach. So let's talk a little bit now. Let's go back to windowing functions, because windowing functions are interesting, fascinating creatures. And what we're going to do is create a view. And this view is actually already created because I was a semi-professional presenter. I do some stuff ahead of time. I wish I could create all these indexes ahead of time and just like swap them in and out, but I'm not that good at things yet. I could have like 40 different databases that just were all set up the way I wanted them, but no. But I got this view, and this view is going to select some columns from the post table and generate a rank of, for each user, I want to get their posts ranked by score, right? By like the high score. So I've got this view, and I'm going to turn on query plans for once ahead of time. Try to be a super professional presenter. And I'm going to run this query, and this is going to be fast. Even though we're doing select star, this is fast, right? Crazy. We did select star, and we still had a good time. And when we look at the query plan, the very, very simple query plan finishes in 9 milliseconds. We seek into our non-clustered index to find owner user ID. All right, oops. Tooltip, come back. We seek in there to find owner user ID, and everything is hunky-dory. Now, what we're going to do, because we're nice people and we like sharing, is we're going to put that query inside of a stored procedure, and we're going to say, you know what, everyone, you can get out there and you can access this view, and you can find users and rank their scores too. But this gets slow. This takes about 6 seconds up there. And things look a little bit different in the query plan. That's no longer 9 milliseconds, and that's no longer an index seek. And now we have, of course, this filter way at the end. So let's talk about the differences between those two things. I don't know why there's 2 spaces there. It's bizarre. Strange things happen sometimes in between demos. They just go boom. They go boom. So when we look at these 2 execution plans stacked one above each other, oops, come on back. There we go. We can see where things went awry. The filter over here, not good. The index scan over here, not good. Index here down here, the index seek down here, good. 8 milliseconds, good. 6.5 seconds, not good. Let's dig in a little bit. So this filter operator, it has a predicate where owner user ID equals that user ID parameter. Now, it's a curious thing that parameters, like what we pass into store procedures, this user ID parameter, can't be pushed past sequence project. So that thing that we generate when we generate a row number for dense rank, lead, lag, anything there's anything that generates this sequence project operator cannot have anything except literal values or constant expressions pushed past it. Parameters, variables, all get stuck here. They can't move down here. We can't use them to filter data over here. We can only use them to filter data when they are literals like this. Now, I know that seems a little bit weird, but those are the rules. This is apparently something that was supposed to get written into SQL Server a long time ago, but just never did. But it's okay, because something that did get written into SQL Server that helps us just fine is inline table valued functions. So these nice functions that return just select queries, returns table, they can take parameters, which is something that views can't do, and they can do things just fine, even inside of a store procedure. Right? So if we pass the parameter from our store procedure here, everything ends up hunky-dory. Once again, we're able to seek into our index. We don't need to filter stuff over here. There's no filter, thank goodness. And this thing goes back to running very, very quickly. So if you have views or, I don't know, anything else, common table expressions, derived tables, any one of those things, and they have windowing functions in them, and you need to do some filtering with variables against those queries, and you find that those queries get very, very slow when you use parameters or variables. This is why. And the better way to use them, the better thing to do is to use an inline table valued function, because these things can accept parameters in a way that allows us to filter earlier on in the execution plan. Yes, brains explode constantly. It's a terrible thing. So the last thing that I want to talk about, I think we still have a couple minutes left, is local variables. And then I have the fully detailed post at this bit.ly link. If you want to go there, you can read all about stuff. But what I want to show you here is just a few quick things about local variables, why they are weird, and why they kind of stink. Now, when we create indexes, we also create statistics, and statistics also, they have all sorts of cool things about them. There's all sorts of good information about, how many rows we sampled, how many steps are in the histogram. And then, of course, we have our histogram itself, which has all sorts of, well, hopefully good up-to-date information about the data in our indexes or in our statistics objects. But when we haul off and we use local variables, when we declare a variable, and then we use it to filter on some data, we don't use the histogram in order to get cardinality estimates. You can see that SQL Server makes a pretty terrible guess here. It guesses that we have 12 rows in the table that match, but that we actually get about 28,000 rows. Now, the reason we get that is because when we use a local variable, we get a less precise estimate from SQL Server about what it's going to do. So if we run all of this together, we can see that SQL Server, its guess for this was 12 rows. And that comes from taking the number of rows that are in our statistics object and multiplying it by all density. So I've got that right here. And if we look at the result of this, it's going to be 11.9, so about 12. So it rounds up to 12. So we get 12 rows from there. And of course, we get the density calculation, which is this thing, 6.9 scientific notation, by running this. And we'll get 6.9 scientific notation back there. So SQL Server does some math. It's not like totally dumb guess, but it's a pretty dumb guess. Now, if we don't have statistics in place for something, and we want SQL Server to make a guess about it, then SQL Server uses even different methods to estimate things. If we're using what Microsoft has taken to calling the default cardinality estimator, which is the new one that got introduced in SQL Server 2014, which is rude, and they shouldn't have done that, because everyone knows that the legacy cardinality estimator is the best cardinality estimator ever, and this one is just kind of blah, whatever. So the guesses that we make here, despite the fact that we get 27,000 rows back from both of these, well, neither cardinality estimator exactly covers itself in glory. The new default cardinality estimator thinks that we'll get 4,100 rows back, right? We can see that if we look at the execution plan, SQL Server, 4,100 for the default, and 266,000 for the best cardinality estimator. But those are the guesses that we get back. So there are slightly different mathematical models involved in that. The default uses some square root nonsense, and the best cardinality estimator ever uses some powerful magic. CBC power right here. We know that it is indeed powerful magic. Now, local variables are usually the cause, or can quite often be the cause of sort of bad cardinality estimates, sort of poor performance. You get this one query plan that kind of stinks for everybody, but we can make them into full-fledged parameters by taking a local variable and feeding it into some dynamic SQL or another store procedure, and just sort of making it better like that. So if you do need to do things like this, if you do need to declare variables inside of store procedures, if you need to, figure out, some thing about someone who did something inside of your store procedure, and you want to use those declared variables in where clauses, or I guess you could use them in join somehow. It wouldn't be pretty, but I guess you could. If you need to use them in where clauses to filter data out, you are generally better off taking those taking those local variables and passing them in to dynamic SQL or other store procedures where they can be treated like parameters, and SQL Server can make accurate cardinality guesses about them. Now, that's about the time that I have here. I know we went a couple minutes over, but I hope you'll forgive me. I hope you had a good time. I hope you enjoyed yourself. Again, I'm Erik Darling. If you want to get in touch with me, you can do that at any of, not those places. You can do it at any of these places. Oh man, you're going to make a liar out of me. And I'm going to have this, I'll have the zip with all the demos uploaded a little bit later today, and I'll have the link sent out for everyone. So you'll be able to download these and run them on your own. But if you want to get in touch with me, I'm over here, all over the place. So thank you for having me, and have a lovely rest of your day.